It's 3 a.m. Your phone buzzes. Production is down. A pod won't start. You run kubectl events, wade through hundreds of normal events to find the one warning that matters, describe the pod, check the replica set, trace back to the deployment, realize a persistent volume claim is missing, write the YAML, apply it, validate the fix. 30 minutes later, you're back in bed, wondering if there is a better way. And here's the gist of it. There is. What if AI could detect the issue, analyze the root cause, suggest a fix, and validate that it worked? What if all 4 phases happened automatically, or at least with your approval, while you stayed in bed? I'm going to show you exactly how to do this with Kubernetes. First, we'll walk through the manual troubleshooting process so you understand what we're automating. Then I will show you an AI-powered solution using Cloud Code and the model context protocol that handles detection, analysis, remediation, and validation. Finally, we'll look under the hood at how the system actually works. We'll take a quick break here to introduce you to JFrog Fly, the sponsor of this video. So here it goes. Automating incident detection and remediation is critical, but there's another piece of the puzzle. Managing the artifacts and releases that flow through your deployment pipeline. That's where JFrog Fly comes in. JFrog Fly is an artifact management solution built for the AI era and designed for small teams. It provides zero config setup. You sign up with your GitHub account, and within minutes, your repositories are connected. For every code repo in GitHub, there's a corresponding repository in Fly with all the releases and packages generating from your source code, bidirectionally linked. The platform offers complete context in one place. Pull requests, issues, change summaries, and contributors are all stored against your releases. This enables agentic release pipelines where agents can locate and perform actions on releases based on their semantic meaning. It works out of the box with your stack. GitHub, GitHub Actions, Kubernetes, Argo CD, and more. You can even manage releases directly from your AI-enabled IDE. JFrog Fly is currently in beta and free, and I repeat, free to use. Check it out, the link below, and see how it fits into your workflow. Big thanks to JFrog for sponsoring this video, and now let's get back to Kubernetes events. Before we dive into the solution, let's talk about the problem. How the hell do we even know when something is broken in our Kubernetes clusters? And more importantly, once we know there's an issue, what do we actually do about it? Now, I'm not talking about Grafana, Prometheus, Datadog, or whatever fancy observability stack you're using for metrics, traces, and logs. We are going straight to the source. We are going to the first place you should look at, long before you even open your observability tools. When dealing with the issues in Kubernetes, there are 4 phases: detect, analyze, remediate, and validate. Actually, that's not for Kubernetes, that's for any situation. Now, let's walk through each one of those. First, how do we detect issues? What I'm about to show you is a simple example. You will need to use your imagination, or better yet, your experience, to extrapolate how much more complex this gets in a production cluster with hundreds of resources and far more complicated scenarios. The simplest way to detect an issue is to check Kubernetes events across all namespaces. You will see a bunch of events here, both normal and warning types. The normal events show routine operations like creating config maps and scaling replica sets, but look at that warning event in the A-team namespace. That's what we care about. It says failed scheduling for a pod because PersistentVolumeClaim called PostgreSQL PVC wasn't found. Now, most of the time, you don't want to wade through all the noise of normal events. You want to filter for warnings. And now let's be honest here. This approach is stupid. It assumes you either already know there's an issue by being clairvoyant, or that you have nothing better to do than sit in front of your terminal watching events all day. If it's the former, congratulations on your superpowers. If it's the latter, I strongly suggest switching to YouTube or Netflix instead. They're much, much more entertaining. We will see a better way to detect issues later. For now, let's pretend we somehow knew there was a problem and move on to the analysis phase. So how do we analyze issues? We know from the event that it's a pod issue in the A-team namespace. So let's check it out. There it is. The pod is stuck in pending status. It is not running and it hasn't restarted because it never even started. We need more details. But here's the thing though. This might not be something we can fix in the pod itself for two reasons. First, that pod might not have been created directly. Some other resource might be controlling it. If we change the pod, that controller will just undo our changes. Now, look at the controlled by field. It shows this pod is controlled by a replica set, but it could have been controlled by a deployment, stateful set, or any number of other resource types. And second, we need to figure out why that persistent volume claim wasn't found. That is not a pod configuration issue. It's not. Now, let's follow the breadcrumbs and check the replica set. According to the events, this replica set is perfectly fine. It did its job. It created a pod. What happens to that pod after creation? Well, that's someone else's problem as far as the replica set is concerned. But notice the replica set is also controlled by another resource, a deployment called PostgreSQL-DB. We need to keep following the chain. Now, the deployment also looks fine. It scaled up the replica set, which is exactly what it should do. If the problem were in the deployment configuration itself, this is what we would need to update. But it's not. At least now we understand the ownership chain. Deployment controls the replica set controls pod. That's important to know, since we eventually need to make changes. Maybe. Who knows? We'll see. Nevertheless, the real question is, why isn't the persistent volume claim there? Look at that. Bingo. There's no persistent volume claim in the namespace. That's our root cause. The pod is trying to mount a PVC that doesn't exist. Now, before we remediate it though, let's make sure the cluster has a storage class available so we can actually create a PVC. There we go. Perfect. We have a standard storage class available and it's even set as the default. We can create a PVC that will use this storage class to provision storage. So how do we remediate this issue now that we know what the problem is? Well, we need to create that missing persistent volume claim. And here's what that would look like. But I'm not going to execute that. We'll see why in a moment. And before we move on, let me quickly touch on validation. That's the fourth phase. After you apply remediation, you validate that it actually worked. Validation is essentially the same process as analysis, except now you're not trying to find the root cause. You're confirming the issue was resolved. You would check the pod status, look at events, follow the breadcrumbs if needed, and make sure everything is healthy. Now, here's the thing. We're not going to execute that remediation manually because there's a better way. Let me show you why this entire process is ripe for automation. Think about each of those four phases we just walked through. Nearly all of them can be automated. For detection, what we need is a Kubernetes controller that monitors events and triggers notifications based on specific criteria. For example, warnings that happen in specific namespaces and are repeated more than, let's say, 3 times. Let the controller do the watching. Now, let's talk about analysis. Automated analysis is already happening in Kubernetes, but only for known issues. Kubernetes handles situations that are defined in advance. For example, if a pod fails, a replica set creates a new one. Controllers manage resources based on predictable patterns. But when there is a persistent issue like the one we just saw, it's caused by unknowns. It's something we didn't predict would happen. That's traditionally why we need people to investigate and figure out the root cause. We need people to figure it out. But do we really need people? How about we change the word people to intelligence? What we actually need is someone or something capable of following the breadcrumbs, analyzing data, comparing it with knowledge base, and doing whatever else needs to be done to figure it out. That intelligence could be you, or it could be AI. Then we have remediation, which is the next phase. Once we find the root cause, we need to create a solution by creating, updating, or sometimes deleting resources. AI can do this as well. It's actually decently good at it. Not as good as analyzing data, but good nevertheless. The key question is, do we remediate issues directly, or do we require someone to review and approve the remediation first? We can apply that same choice to AI. We can let it fix issues automatically, or we can insist on it showing us the proposed remediation and waiting for our approval. And once remediation is approved and applied, it follows whatever standard process you're using to manage resources. That could be kubectl, or Helm, or GitOps, or workflows, or anything else. Validation is pretty much the same as analysis, except this time we are not looking for the cause of the issue. We are confirming that the remediation actually worked. Now, I've been saying that when issues are based on unknowns, we need to involve humans. And sure, we should strive towards never, and I repeat, never having unknowns. But that's often not possible. Shit happens. And that's not up for debate. It just happens. But here's a better way to think about it. We need intelligence to analyze, remediate, and validate the issues. Today, that intelligence can be you, or AI, or more likely, both of us working together. And when I say AI, I really mean agentic AI. If there is something large language models are exceptionally good at, it's crunching and analyzing data. When you connect them with agents, they can request execution of tools that provide them with data, or even remediate the issues if we choose to let them. So let's stop talking theory, no more, and see this in action. Let me show you an example. We're going to ask an AI agent to troubleshoot the same issue we just walked through manually. I'm going to start Cloud Code with an MCP configuration. This MCP has a tool that handles the entire process of analyzing, remediating, and validating issues. Inside that MCP, there's an agent working with an LLM to do the analysis and figure out what's wrong. All we need to do is to state the problem and later confirm whether the suggested remediation looks correct. Or, as we'll see in a moment, we can connect it to a controller so even detection can be automated. Now, for now, we are skipping detection because we already know there's an issue. So let's just tell the agent what's wrong. Look at that over there. The agent analyzed the issue, followed the same breadcrumbs we did manually, identified the root cause with 99% confidence, and provided a remediation proposal. We can execute it automatically through the MCP, or we can do it ourselves via the agent we are in right now. In my case, that's Cloud Code, or any other way. If you let the MCP handle it, it will also validate that the fix worked. Nevertheless, I'm going to skip the remediation for now because we are missing the first step, detection. So let me show you how we can automate that as well with the Kubernetes controller. This is a remediation policy custom resource. It tells a Kubernetes controller what events to watch for. In this case, we are watching for warning events with a failed scheduling reason on pods. When the controller detects a matching event, it sends a request to the MCP endpoint specified here, over there. The MCP does the analysis, remediation, validation. That's the one we saw earlier. You can configure things like confidence thresholds, maximum risk levels, rate limiting, and even Slack notifications. So let's apply it. And now let's just wait a few moments. Just be slow and wait. Give some time for the controller to detect the event, to fire a request to the MCP, and to let it handle everything. And now, let's see. If this worked, we should see the pod running and the PVC created, right? Look at it. Perfect. The pod is running and the persistent volume claim has been created and bound. The controller detected the issue, the MCP analyzed it, remediated, and validated that the fix worked. All 4 phases, completely automated. If we had Slack integration enabled, we would see notifications with the analysis and suggested remediation for manual mode, or the analysis, remediation commands, and validation results in case of the automatic mode. Now, that's pretty damn impressive when you think about it. But you're probably wondering how all of this actually works behind the scenes. We just saw it in action, but how does this actually work under the hood? Let's break down both the MCP and the controller. Let's start with the detection. A user figures out through whatever means that something is wrong and provides information about the problem to their coding agent, like Cloud Code or Cursor or whatever they are using or you are using. The coding agent then sends that to the MCP. This is manual detection where the user initiates the process. The alternative, as we just saw, is automated detection through the controller, which we'll get to in a moment. Next is analysis. The MCP has its own internal agent that works with an LLM to gather information and analyze the issues. The MCP agent takes the user's intent and enhances it with additional context. This includes a list of tools the LLM can use to gather more information and instructions for the LLM to perform a loop until it analyzes the issue and figures out the root cause and recommended remediation. Once that's done, once the loop is finished, once it's finished gathering all the information it needs to deduce what's wrong, it also performs a dry run to validate the solution. So, the gathering of data and the dry run happen through a loop. The LLM requests tool execution. The MCP agent executes those tools like kubectl get, kubectl describe, kubectl events, and so on and so forth against Kubernetes, which returns data. The agent adds the outputs to the context and sends it back to the LLM. This continues looping and looping until the LLM responds with, "Hey, you know what? I am done." Importantly, those tools are all read-only. The LLM never, and I repeat, never requests changes to the Kubernetes cluster. That's a critical security constraint. Once the LLM finishes the loop, it responds back to the MCP agent with the analysis and suggested remediation. The MCP agent then sends this back to the coding agent, which presents it to the user, to you. Now, for remediation, the coding agent presents the analysis and suggested remediation to the user. The user has choices. They can apply the remediation manually by executing kubectl apply, or making changes to files in Git and letting GitOps sync them, or using whichever other process they prefer. It's up to the user. But, alternatively, the user can tell the coding agent that the remediation should be done by the MCP. Just go back there. Now, when the MCP handles remediation, the MCP applies the suggested commands directly to Kubernetes. This is an important security model. The user reviews the suggested remediation first, then the MCP, the code in MCP, not AI, the code executes it. The LLM and MCP agent never, and I repeat, never execute remediation themselves. Remember, they only have access to read-only tools. Write operations are always done by the MCP's code, and only after user approval, unless you choose to remediate it automatically. Finally, validation. If the user delegated remediation to the MCP, once it's done, the MCP performs validation to confirm the remediation worked. This uses essentially the same analysis process we discussed earlier with the MCP and LLM looping to get data from Kubernetes. Except, this time, the goal is not to find the root cause. It is to confirm the issue was resolved. And once validation is complete, the MCP sends the validation results back to the coding agent, which presents them to the user, to you. Finally, how does the controller work? The controller monitors specific events defined in the remediation policy resource, like the one we saw earlier. When an event matching the filters is fired, the controller sends a request to the MCP server with information about the potential issue, along with the remediation mode, confidence threshold, maximum risk level, and other configuration. At the same time, if Slack notifications are enabled, a notification is sent indicating that a potential issue was discovered and that analysis is in progress. The MCP performs analysis, and now there are two paths depending on the configuration and the MCP's assessment. The manual remediation path kicks in when the MCP decides not to auto-remediate. This happens for three reasons. 1, the confidence is below the threshold. 2, the risk is above the threshold. Or 3, that the event type is configured for manual mode. When manual remediation is required, the MCP responds back to the controller with just the analysis and the suggested remediation. The controller sends this to Slack, and now it's up to the user, to you, to apply the remediation. Review it, check whether it's okay, do it. The automatic remediation path happens when the confidence is high enough, the risk is acceptable, and the event type allows automatic mode. In this case, the MCP applies the remediation and validates it against Kubernetes. When that is done, the MCP responds back to the controller with not just the analysis, but also which remediation commands were executed and the validation results. The controller sends all of this to Slack. In both cases, we get full visibility through Slack about what was discovered and what actions were taken or recommended. So, if you want to try this out yourself, check out DevOps AI Toolkit. That's the MCP that handles analysis, remediation, and validation. There's also .ai controller, which does the detection and triggers the whole process. Both are open source. Use them, fork them, create the issues, or do whatever else you want with them. They're yours to experiment with. So, back to the beginning. You remember that 3 a.m. phone call from the very start? That doesn't have to be your reality anymore. We moved from manual troubleshooting that takes 30 minutes of following breadcrumbs through kubectl commands to AI-powered remediation that handles all 4 phases. Detection through a Kubernetes controller, analysis through an LLM agent loop, remediation with your approval or fully automated, and validation to confirm the fix work. The key insight here is that we don't need to predict every possible failure scenario. We need intelligence that can investigate unknowns, and that intelligence can be AI. The security model is solid because the LLM only has read-only access. Right operations require either your explicit approval or confidence and risk thresholds you define. You decide whether you want manual approval for every fix or automatic remediation for low-risk issues with high confidence. You can use DevOps AI Toolkit as is if it fits your needs. It's green, it's new. Your own risk. You can deploy the MCP, set up the controller, configure your remediation policy, and you're done. Or use it as a blueprint. Study how the MCP agent loops with the LLM, how the controller watches events, how the security model keeps right operations isolated from AI decision making. Take those patterns and build your own solution that fits your infrastructure, your tools, your risk tolerance. The code is out there. The architecture diagrams are in this video. The point is, you have options beyond debugging Kubernetes at 3 a.m. Thank you for watching. See you in the next one. Cheers.